In episode 69, titled Voice/Video Signals, SIP, WebRTC, RTSP, H.323 as scenario hints, the focus is on treating protocol names as clues rather than as trivia, because the exam often uses these acronyms to hint at traffic behavior, constraints, and what the network must do well. When you see these protocol names in a scenario, the question is rarely asking you to recite definitions in isolation. Instead, it is usually signaling that the traffic is real-time, interactive, and sensitive to latency and jitter, or that it involves streaming media with specific control patterns. These protocols also carry implications about encryption, traversal through firewalls, and what breaks when middle boxes try to inspect or rewrite traffic. If you can interpret the protocol name as a signpost, you can make better design choices about quality of service, segmentation, and monitoring, even when the scenario is light on details. The exam rewards that inferential skill because it mirrors real troubleshooting, where protocol clues guide your first assumptions. This episode builds that interpretation framework so you can recognize what the protocol implies and what the likely network priorities should be. The aim is to help you answer scenario questions by reading the hints embedded in the protocol list. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Session Initiation Protocol, commonly called SIP, is signaling for voice and video session setup, meaning it is used to establish, modify, and end real-time sessions. Signaling is the control plane portion of communication, where endpoints negotiate who is calling whom, what codecs will be used, and where media should flow. SIP itself is not the actual voice or video stream, but it is the protocol that coordinates how that stream will be carried. This distinction matters because troubleshooting often involves separating call setup works from media quality is good, and SIP is primarily involved in the setup and negotiation portion. The exam often includes SIP to indicate voice over Internet Protocol environments, soft phones, or unified communication systems, all of which share similar sensitivity to delay and loss. SIP also implies that there may be separate media streams using other protocols, which means security rules must allow not only the signaling but also the negotiated media paths. In many environments, SIP interacts with network address translation and firewall policies, which can create failure modes where calls connect but audio is one way or absent. When you see SIP, you should think session negotiation plus downstream media requirements, and you should be ready to consider real-time quality constraints. Web real-time communication, commonly called WebRTC, is browser-based real-time communications that uses encrypted media, and it is often used for voice and video directly within web applications. WebRTC is designed to work across diverse networks, including those with network address translation, and it typically uses modern encryption practices for the media streams. The exam uses WebRTC as a hint that the application is interactive, likely uses peer-to-peer media paths when possible, and may fall back to relay mechanisms when direct connectivity fails. Because WebRTC is built for browsers, it is often associated with rapid session establishment, adaptive bitrate, and dynamic behavior depending on network conditions. The encrypted media aspect matters because traditional deep inspection tools may not be able to see inside the media stream, and attempts to intercept or rewrite encrypted traffic can break connectivity or degrade quality. WebRTC can also be sensitive to firewall traversal constraints because it may require specific types of connectivity for media to flow consistently. When you see WebRTC in a scenario, you should think real-time encrypted media with traversal challenges and a strong need for predictable latency. It is a strong signal that quality of experience depends on network stability and that blunt security controls can create subtle failures. Real-time streaming protocol, commonly called RTSP, is a control protocol for streaming and camera feeds used to manage playback, pause, and stream setup for media streams. RTSP is often associated with surveillance cameras and streaming devices, where a client requests a stream from a server and uses RTSP commands to control the session. The exam uses RTSP as a hint that the traffic pattern may be one-to-many or many-to-one in surveillance environments, where multiple viewers may request streams from cameras or from a central video management system. RTSP itself is a control plane protocol, and the actual media may be carried by a separate transport stream, which means firewall rules must often consider both control and media. Camera feeds can be continuous and bandwidth-heavy, which has implications for network capacity and for quality of service planning if the same network also carries interactive voice traffic. RTSP scenarios often include storage, archiving, and remote viewing, which can generate traffic bursts when users scrub video or request high-resolution streams. When you see RTSP, you should think streaming control for video sources, often cameras, with sustained media flows that can compete with other traffic. It is a signal to consider bandwidth and segmentation as much as latency. H.323 is a legacy suite for conferencing that is still found in enterprises, especially in environments with older video conferencing equipment or long-standing unified communications deployments. Calling it a suite matters because H.323 historically encompasses multiple components for signaling, control, and media negotiation, which can make it more complex to traverse security devices and network address translation. The exam includes H.323 as a hint that the environment may have older infrastructure, fixed conferencing rooms, and integration requirements that were designed before modern web-friendly approaches became common. Legacy protocols can also be sensitive to inspection and rewriting because some implementations embed addressing information in ways that complicate firewall traversal. This often creates practical constraints where a system works only when specific policies are applied, or where upgrades must be done carefully to avoid breaking existing conferencing workflows. When you see H.323, you should think legacy conferencing behavior and the need for careful policy design to support required signaling and media. It is also a clue that the network team may be dealing with a mix of old and new, which complicates standardization. The key is not to dismiss it as outdated, but to recognize it as a scenario signal that real enterprise environments still carry. The common thread across these protocols in exam scenarios is that real-time traffic is sensitive to latency and jitter, and that sensitivity drives network design priorities. Latency is the time it takes for packets to travel, and jitter is the variability in that time, and both affect how voice and video are perceived. Real-time conversations can tolerate only limited delay before users talk over each other, and they can tolerate only limited jitter before audio becomes choppy or video becomes stuttered. Packet loss and reordering also matter, but jitter often becomes the visible culprit when networks are congested or when traffic is competing with bulk transfers. The exam expects you to treat real-time flows as needing consistent delivery, not just high throughput, because you can have plenty of bandwidth and still have poor voice quality if latency spikes unpredictably. This is why these protocols are used as hints, because they imply interactive sessions where quality is experiential rather than transactional. When you see them, you should prioritize stability, predictable paths, and congestion avoidance. Designing for real time is designing for consistency. Quality of service matters because it is the mechanism used to prioritize media traffic over bulk transfers when resources are constrained. Prioritizing media does not mean starving other traffic, but it does mean ensuring that latency-sensitive packets are not stuck behind large downloads or backup traffic during congestion. Quality of service strategies often classify traffic into classes, allocate queuing behavior, and reserve bandwidth for critical flows. The exam uses voice and video protocol hints to push you toward considering quality of service because without prioritization, real-time traffic competes unfairly with traffic that is not harmed by delay. Bulk transfers can tolerate delay because they are throughput-oriented, but voice and video cannot because the user experiences the delay immediately. Quality of service also requires end-to-end consistency, because prioritizing on one segment and ignoring another can still result in congestion and jitter at the weakest link. When you design for quality of service, you think about where congestion occurs, how queues behave, and how to preserve low jitter delivery. The exam expects the high-level understanding that media should be treated as high priority and that the network should enforce that priority across critical hops. When you can connect protocol hints to quality of service decisions, you are using the scenario clues correctly. A scenario where video quality drops due to jitter spikes often reflects congestion or queuing behavior rather than a simple bandwidth shortage, and this is a common exam pattern. Users may report that video freezes, audio becomes robotic, or frames drop during busy periods, which suggests that packet arrival timing is inconsistent. The underlying cause can be competing traffic, such as large file transfers, software updates, or backups sharing the same links and causing queue buildup. Even if average bandwidth usage appears acceptable, microbursts and queue depth can create jitter that disrupts real-time streams. This scenario is where quality of service prioritization and traffic segmentation matter, because you want media to avoid being delayed by non-urgent transfers. It also highlights the importance of monitoring beyond simple utilization, because jitter and loss are not always visible through link throughput graphs alone. The exam expects you to recognize that jitter spikes are a symptom of inconsistent delivery, and that mitigation often involves prioritization, controlling congestion, and ensuring adequate capacity at bottleneck links. When you interpret video degradation as a jitter issue, you choose controls that restore stability rather than chasing codec settings blindly. One pitfall is blocking needed ports or breaking encrypted media through inspection, because voice and video protocols often rely on negotiated media paths and encryption that do not tolerate interference. Firewalls and security devices that block unknown ephemeral ports can prevent media from flowing even when signaling succeeds, causing symptoms like calls that connect but have no audio or video. Attempts to inspect or intercept encrypted media can also break sessions, especially with protocols designed to enforce end-to-end encryption. Even when inspection does not break the session, it can introduce latency and jitter by adding processing delay, degrading quality. The exam tests this by presenting scenarios where the network team applied strict inspection or port restrictions and media stopped working or quality degraded. The correct reasoning is to allow required signaling and media flows in a controlled way, balancing security with functional requirements for real-time encrypted traffic. This often includes understanding that control plane and media plane may use different paths or ports, and that blocking one can produce partial failures that are confusing. When you see encryption and real-time together, you should be cautious about middlebox interference. Supporting these protocols often means careful policy design rather than blanket inspection. Another pitfall is ignoring bandwidth planning for concurrent calls, because real-time media scales with the number of simultaneous sessions, and that can saturate links quickly. Each call or video session consumes a certain amount of bandwidth depending on codec and resolution, and a busy office can have many concurrent sessions during peak collaboration periods. Surveillance systems can also generate large, continuous streams, and when combined with voice and video conferencing, the aggregate demand can exceed what uplinks and wide area links can support. The exam expects you to recognize that bandwidth planning must consider concurrency, not just per session requirements, because the failure mode appears as widespread degradation during busy hours. This is also where segmentation helps, because separating camera traffic from voice traffic can prevent one workload from consuming resources needed by another. Ignoring concurrency leads to designs that work in tests and fail in production, especially during events or emergencies when call volume spikes. When you plan bandwidth, you plan for peak concurrent usage and you identify bottleneck links explicitly. Real-time quality depends on having both priority and sufficient capacity. Quick wins include segmenting voice traffic and monitoring mean opinion score style indicators so you can detect quality degradation early and correlate it with network conditions. Segmenting voice traffic means placing voice endpoints in dedicated VLANs and applying consistent quality of service markings and policies to those segments, making prioritization more reliable. Monitoring quality indicators helps because voice and video issues are often subjective, and metrics provide objective signals such as jitter, packet loss, and call quality scoring. Mean opinion score style indicators are a way to express perceived voice quality based on measurable network parameters, and tracking them over time reveals whether changes improve or harm user experience. Monitoring also helps differentiate network issues from application issues by showing whether jitter and loss correlate with specific links, times, or congestion events. The exam rewards answers that include monitoring because it demonstrates that you will validate quality rather than assume it. Segmenting and monitoring together create a feedback loop where you can tune quality of service policies based on real evidence. When you treat voice and video as monitored services, not just traffic types, you improve reliability and troubleshooting speed. A useful memory anchor is signal, media, sensitivity, prioritize, monitor, because it maps protocol hints to design actions. Signal reminds you that protocols like SIP and RTSP often represent the control plane that sets up sessions. Media reminds you that the actual audio or video stream is what carries user experience and may be separate from signaling. Sensitivity reminds you that real-time media is sensitive to latency and jitter in a way bulk transfers are not. Prioritize reminds you that quality of service and traffic segmentation are used to protect media during congestion. Monitor reminds you that you need objective indicators such as jitter and quality scoring to detect issues and validate improvements. This anchor is useful on the exam because it turns a protocol list into a predictable chain of reasoning. When you see SIP, WebRTC, RTSP, or H.323, you can immediately ask what signaling is required, what media will flow, how sensitive it is, how it should be prioritized, and how it should be monitored. That is exactly how scenario-based questions are meant to be approached. When you can apply the anchor, you are using protocol names as hints effectively. To apply this, imagine being given a protocol list and asked to infer application type and plan, and start by mapping each protocol to its typical use. SIP suggests voice and video call setup. WebRTC suggests browser-based real-time communications with encrypted media. RTSP suggests streaming control, often tied to cameras. And H.323 suggests legacy conferencing systems. From that mapping, you can infer whether the environment is unified communications, surveillance streaming, browser conferencing, or a mix, and you can plan network priorities accordingly. If the list includes SIP and WebRTC, you plan for interactive, real-time sessions with encryption and traversal constraints, emphasizing quality of service and careful security policies that do not break media. If it includes RTSP, you plan for sustained streaming traffic that may be bandwidth-heavy and that should be segmented to avoid harming voice and conferencing. If it includes H.323, you plan for legacy behaviors and potentially stricter requirements for allowing signaling and media flows through firewalls. The exam expects you to translate these hints into priorities like latency protection, bandwidth planning, and monitoring, not just to label the protocols. When you can infer workload and then choose controls, you demonstrate the intended skill. To close episode 69, titled Voice/Video Signals, SIP, WebRTC, RTSP, H.323 as scenario hints, the key is that protocol names are scenario clues about traffic type, session behavior, and what the network must protect. SIP and H.323 point toward voice and conferencing signaling with associated media flows. WebRTC points toward browser-based real-time encrypted media with traversal constraints, and RTSP points toward streaming control often associated with camera feeds. Real-time traffic is sensitive to latency and jitter, so stability and prioritization matter more than raw throughput alone. Quality of service and segmentation help protect media flows from bulk transfers, while monitoring indicators like jitter and call quality scoring provide objective evidence of user experience. The most common pitfalls are blocking the needed signaling or media flows and breaking encrypted sessions through over-aggressive inspection and underestimating bandwidth needs for concurrent sessions. Quick wins like voice segmentation and quality monitoring improve both performance and troubleshooting speed. Your rehearsal assignment is a traffic suitability rehearsal where you take one protocol list, state what application it implies, and then describe how you would protect it through prioritization, bandwidth planning, and monitoring, because that is exactly how the exam expects you to interpret these protocol hints. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.